Welcome back. In this and next few lectures, we will be addressing a new topic, which is probably the final section on second law. This theme is associated with exergy. In the previous lecture, we looked at entropy balance and entropy generation. Entropy, as opposed to mass or energy, is not a conserved quantity. Okay, so we have an entropy generation term in order to write an entropy balance. So this makes it different from mass and energy conservation. And there are fundamental reasons why entropy is not a conserved variable. However, even though it is not a conserved variable, we can write a balance equation just like we wrote for energy and mass. So for example, this in a closed system or in a flow system, we can associate entropy, for example, in this case, with a particular inlet and outlet stream and entropy that comes in from the surroundings and so on. And we can write in with via different case studies, we demonstrated how we can write a balance equation for entropy. A particularly good example to understand entropy generation is this simple heat transfer issue. Here we looked at heat that is transferred, and for heat to be transferred, temperature difference is a prerequisite. So the heat that gets transferred is the same across this interface. However, the temperature is different from this point and at this point of the interface. So because of this finite temperature difference, there is entropy generation term, and we had elaborated on this example in the previous lecture. So it's entropy generation, although it looks mystical, once you look at certain case studies, you understand why there is this term called entropy generation. And overall, again, I emphasize, to get a better feel for entropy, it's good to have a good understanding of microscopic interpretation of entropy. In this lecture, we will start with this topic on exergy analysis. What is the overall objective when we do an exergy analysis? This is a topic that is addressed typically and primarily in engineering thermodynamics textbook. In fact, if you go to chemical thermodynamics, a chemistry textbook, or a physics class, you will not even hear about this term called exergy. However, it has a lot of engineering utility. So the major objective here is, how do you utilize energy reserves towards optimally achieving an engineering objective? Whenever we want to do some work, for example, here you have air. Using this air, we can do work, obtain work. However, if certain properties of the air are the same as the ambient atmosphere, then the work potential of the system is zero. For example, in this case, the temperature of the air is the same as the temperature of the ambience. The pressure is also the same. So there cannot be heat transfer, there cannot be mechanical forces on either difference in mechanical forces on either side, which will facilitate pumping of liquids. And the velocity is zero. There's no kinetic energy in the system, and the center of mass is approximately at zero with respect to the ambience. Therefore, it has no potential energy. So overall, this system has no potential to do work. So such a system is called a dead state. In other words, a dead state is that which is in equilibrium with the ambient atmosphere. So all the Exergy analysis we'll be undertaking will be on a system which is not in a dead state. Okay? So if a system is a dead state, the potential to obtain work is zero. Therefore, we won't be looking at such a state. But the dead state has an important role to play in our Exergy analysis, because we want to look at the work potentials of systems that are not in dead state. So dead state is one of the limit for us to look at the work potential of systems. So this dead state, we refer to the dead state by saying that it has no exergy or no availability or no available energy. These are all equivalent terms that have been used in different parts of the world and in different textbooks. Okay, so overall, all these things refer to the work potential of a system: exergy, availability, available energy. There are also related terms called lost work and so on. All these things are connected with exergy. So all these refer to work potential of a system. So Exergy provides a bound on work a device can deliver within thermodynamic constraints. So we are not violating first law and second law. And we ask the question, what is the maximum work that can be generated from a system or from a device? That is the overall objective of Exergy analysis. For example, let's take the simplest case. Supposing a system has a particular potential energy. For example, here there's water, which is at a certain elevation. When you allow the water to drain through this pipe, this potential energy is converted to kinetic energy that can rotate a shaft and so on. The entire potential energy, okay, can be converted to work. Okay, so the exergy of this mass of water at a particular elevation is 100%. Okay, but however, this might not be the case in many systems. Out of the total energy available in the system, only part of the energy can be utilized for obtaining work, and some part cannot be utilized for obtaining work. Okay, so that part that is utilized for obtaining work is associated with this quantity called exergy, and some part is not that's not going to give you any work is called unavailable energy, and this is associated with exergy availability or available energy. Things will become more clear as we look at some examples. We had already looked at the importance of work obtained from reversible processes, and we stated that when there is a system goes from initial to final state, and if there are two paths to going from an initial state to final state, and if one of the path is reversible and if the other path is irreversible, we stated that the work that is obtained in the reversible path is the highest, okay, compared to any other irreversible path. Okay, so how did we prove this? We stated if this is not the case, such a system, this being reversible, if we reverse it, we will obtain work by exchanging heat from one reservoir, which is a violation of Clausius inequality. So we had earlier proved this in some previous lecture. You can look at the proof for this statement. But the statement we are making here is that if there is a reversible path that is work generating, that generates the maximum amount of work for the same initial and final state compared to any other path, any other irreversible path. So the work that is obtained from the reversible path minus the work that is obtained from other paths, which is less than work reversible, is a measure of irreversibility. Okay, so whenever there is a difference, it's a measure of irreversibility. So although that the work from a reversible path provides an upper bound, please note that this is an abstraction of a process. Okay, it is asymptotic to reality, right? Asymptotic. This is a path that can be only reached asymptotically if the changes are made infinitesimally. Okay, so it provides a bound, but all real processes are not reversible, and the deviation from these two quantities is a measure of irreversibility. There are other ways to think about irreversibility. For example, if there is a heat transfer from a thermal reservoir to another thermal reservoir, this temperature differential provides the maximum work that can be obtained from a heat engine. Okay, what kind of a heat engine? This is a heat engine operated reversibly. It's a Carnot heat engine. Supposing once we know these two temperatures of the reservoirs, we can get the maximum work that can be obtained by running a Carnot reservoir between these two reservoirs. In this case, for these two temperatures, the maximum work is 375 kilowatts. However, what you get from the heat engine that is being operated is, let's say, 180 kilowatts. The difference between these two, that is this abstract reversible Carnot heat engine, this work that is obtained from such a heat engine minus the work that is obtained from a real heat engine is a measure of irreversibility in the system. So in this case, 375 minus 190 is a measure of irreversibility in the system. So the greater is the difference, greater is the irreversibility. And of course, if the difference is zero, we say irreversibility is zero and the process is operating reversibly. There is an interesting example in your textbook that emphasizes a particular issue of how to utilize heat. Okay, so whenever we talk about exergy, we are talking about work transfer or work potential. In this case, that's not the central quantity, but a related topic of how to best utilize heat is being addressed in this case. For example, you have a hot block of iron, let's say, which is at 200 degrees centigrade. And our engineering objective is to heat a room that is at a lower temperature. Let's say you want to keep the room at 27 degrees centigrade. Okay, so our objective is to heat the room. You can ask the question, how best to utilize the internal energy available in this iron block, which is at 200 degrees centigrade, to heat the room. Okay, so if that is the way you define this problem, one way of doing this is straightforward. Okay, you put the iron block at this higher temperature inside the room, and the heat transfer, because of this finite temperature difference, is one way of heating the room to keep the room hot. But is this the only way, or is there other beneficial way of utilizing heat is the question. So supposing instead of directly transferring this heat, okay, you are drawn a heat engine. Supposing in this case, the heat engine was run by utilizing the heat that is transferred from, let's say, 200 degrees centigrade to 27 degrees centigrade. Between these two, let's say, thermal reservoirs, you ran a heat engine, and that provides a way of obtaining work. Okay, so what does this indicate? Okay, so let's understand this thing notation clearly. As the temperature is being cooled from 200 degrees centigrade to 27 degrees centigrade, heat can be transferred from this high temperature source, that is the ion heating block, to your surrounding, which is at 27 degrees centigrade. Okay, so till it reaches 27 degrees centigrade, till the temperature of the ion block reaches 27 degrees centigrade, there is a finite temperature difference between ion and the surrounding. So because of this finite temperature difference, there is heat transfer possible, and that heat transfer is not a direct heat transfer. The heat is getting transferred via a reversible heat engine. Because the heat gets transferred via a reversible heat engine, you can obtain some work, and that work can be utilized for pumping heat from the ambient, which is at 5 degrees centigrade, to air, which is inside the room. Okay, so this work that is obtained by running a heat engine between ion block and this surrounding, this work can be utilized for pumping heat, running a heat pump, okay, between this temperature, which is lesser, the temperature of this ambience is lesser than that of the room, but because of this work, you can run a heat pump, and you can, in principle, transfer more heat into the system. Okay, so that is the advantage of not transferring heat directly from the ion block to the room, but if this heat transfer is accomplished via a heat engine, the work that is utilized, work that is generated, can be utilized for running a heat pump. Okay, so what is that we have done? We have tried to answer this question, heating the room. Okay, so if that is our engineering objective, how best to utilize the internal energy available in this heating block is what is being addressed here. So this case study that is obtained, that is presented in your textbook, and also related points are also mentioned in other textbooks that is typically used in engineering thermodynamics. So time and again we ask the same question: if a body is at a high temperature, instead of directly transferring heat, okay, when you do that, you lose the opportunity to obtain work from the system. Okay, so to best utilize this heat, okay, so it is important to transfer heat from a high temperature source via a power cycle, via a heat engine, such that you can obtain some work that can be used for raising a mass, running a shaft, paddle work, or some power cycle. Okay, so this is the point that's being emphasized. Instead of direct heat transfer, you accomplish this heat transfer via heat engines so that you can get work out of the system. So in contrast to other examples, we just looked at heat transfer and we suggested an alternate pathway for heat transfer. So there are other metrics that are utilized for characterizing a process. For example, here we are looking at the same sink temperature. However, your source temperatures are different. Because of the source temperature differences, you can have different maximum theoretical efficiency. Okay, so here your source is at a higher temperature, your theoretical efficiency obtained from Carnot analysis is 70%. Here it's about 50%. However, your actual efficiency is only 30%. It's not this maximum theoretical efficiency. Okay, so this difference between the actual efficiency which you have in your device and the theoretical maximum is a measure of irreversibility. For example, if your reversible efficiency is 50%, theoretical maximum that you can achieve, but your thermal efficiency, this TH refers to thermal efficiency, is let's say about 30%, your so-called second law efficiency is 60%. Okay, so these are different metrics for calibrating the way you operate the device. Okay, so the so-called second law efficiency, there are lots of different textbooks have defined these metrics in slightly different way, but each have certain utility more than the term. Let's look at what is being computed. Okay, so here, what are we computing here? So you're computing the useful work that you obtain, okay, in a real device, divided by the maximum work that could have been obtained in a reversible heat engine. Okay, so that is a measure of efficiency, the measure of reversibility. Likewise, eta thermal efficiency divided by eta theoretical efficiency of a reversible heat engine. Okay, so that is also a measure of metric of irreversibility. When you transfer heat, as I said, from across a finite temperature differential without passing it through a heat engine, then that is in a way, the worst possible way to utilize heat. Okay, so you have you didn't get any amount of work with this heat transfer. Okay, so in some way that is the most ineffective heat transfer because you didn't get any work out of such a heat transfer. But sometimes in real process, this might actually happen. Okay? All we are saying is that's not the best utilization of thermal energy available at a high temperature. Okay? This is very similar to the question we are asking is similar to what we did in the thermal energy available in the iron block. Okay, whenever you transfer that heat via a heat engine, you can get some work, and that can be further utilized in some other manner, either for heat pump, as we saw in the previous example, or some other purpose. So again, there's another example from your textbook. Here we say that there is a resistance heater. The advertisement states that the COP is 1 or 100%. What exactly we mean? We mean that all of the work, this work, which is obtained from the electrical grid. Okay, so this electrical heater is plugged into an electrical socket. So this work is obtained from an electrical grid, is completely converted to heat. Okay, so is that the best way of operating this, or is the efficiency really 100%? Okay, the advertisement states it is a device of 100% efficiency, but all that 100% efficiency means that all the work can be transferred to heat. So there are other ways of analyzing this device. Let's look at the other ways of analyzing the device. So here we calibrate the efficiency by computing a quantity this particular quantity. This quantity is a ratio of two quantities. One is at the denominator is the exergy expended. So what is the quantity at the denominator? That is the exergy expended. By exergy is the work potential. So what is the exergy expended? This is the work that is obtained from the electrical grid. And then what is the exergy that is recovered? By expending this electrical work, you obtain some heat which has certain work potential. So how do you compute that work potential? The heat that is generated from this electrical resistance, if transferred between two temperature reservoirs, this is the temperature of the high temperature reservoir, this is the temperature of a low temperature reservoir, and if you run a heat engine, the maximum work that can be obtained is the work potential. So you can compute that and divide it by this. So what from this equality, this goes away and you get this term. So that is a measure of efficiency metric of this device. So you can put in some numbers, and we can also get the same number two different ways. And the reason for it, let's look at it. Supposing I calculate the COP of a heat pump that is operated between these two temperatures. We had already derived this formula. You get this particular value. An efficiency metric is the COP of the device as is claimed here, divided by the COP of a heat pump. You get 3.7%. That's exactly the number you get from this quantity 2 if you put these two temperatures. So what is the next topic we'll be looking at? We'll be looking at more quantitative examples of Exergy analysis.